This lecture is on applications of right triangle trigonometry. So starting with a little vocabulary, the angle of elevation is defined as the angle going from horizontal up to a point, so it's this angle in here. Angle of depression is defined as horizontal and then going down to some point. So angle of depression from B to A is given by this angle. Angle of elevation from A to B is given by this angle. And note that these angles are congruent because they're alternate interior angles on these two parallel horizontal lines. So looking at some examples in the book, we see just a simple example solving a right triangle before we get into more word problems. Here we have triangle ABC. We know angle A is 34.2 degrees, side B is 19.4. If you want to find side A, this is an opposite, this is an adjacent compared to this angle, so you can use tangent. Tan A is little a over little b, so A is b tan A. You plug in your values. If you want to find C, this is a hypotenuse, B is an adjacent, so you use cosine. So here's your equations down here. Here again, angle of elevation, angle of depression. So now we put it in the context of a word problem. Here we have a building with a ladder against it, and this angle that the ladder is going up is 72 degrees. The ladder itself is 110 feet long. Note that the ladder is going to be the hypotenuse in this triangle ABC. And we want to find out how high the ladder will be able to reach, which is side A opposite angle A. So we have this angle 72 degrees, this acute angle. We have the opposite side, side A. We have the hypotenuse 110. Opposite over hypotenuse is sine. So we have sine of big A is A over C. This is the equation we would use. This gets a little bit more involved now, where from this single point, we have an angle of elevation up to the top of this smokestack of 53 degrees. Angle of elevation up to the top of the building on which the smokestack sits is only 35 degrees. The distance away is 200 feet. So how tall is just the smokestack? So looking at this smaller triangle below, the smaller right triangle, we can say that tangent of 35 degrees is A over 200, and we'd be able to solve for A that way. Looking at the larger right triangle, we could say that the tangent of 53 degrees is the opposite, which is now A plus S over the adjacent 200. So we have these two equations. First, we could solve it for A. Once we know A, we can plug it into this equation and solve for S, as is shown down here. Now we have a situation where we've got this pool that's 20 meters long, 12 meters wide, though that doesn't really have an issue in this problem. And we want to find the angle of depression for the slant of the pool, given that this is 1.3 meters and it's 4 meters of depth. So really we only care about the 2.7 meters down here. So we've got an adjacent of 20 meters, an opposite of 2.7, and we want to find the angle, so opposite over adjacent's tangent. We don't know the angle this time, so we would be using arctan or inverse tan. Okay, other vocabulary involves what are called bearings. Now, bearings are based on this idea of 0 degrees is north, and we go in a clockwise direction. So in some ways, it's similar to, but a little different from your unit circle. So that's why it can be a little bit confusing. So let's start over here with a few examples. So we have north is 0 degrees, and east then would be 90 degrees. South is 180 degrees. West is 270, and then you get back over to north at 0 degrees. So just a few samples. If we draw off in this direction right here, let's suppose that this angle here is 65 degrees. You could say this is north 65 degrees east. Of course, the complementary angle in here is 25 degrees, so alternatively we could say east 25 degrees north, though usually north or south is given first. So this means that you head north first and then go 65 degrees in an easterly direction, whereas something, say we're coming down here, and let's say this is now 20 degrees, you could say this is south 20 degrees west. We start south and head 20 degrees to the west. If we do something like, say, southeast, then that implies that this is exactly 45 degrees on either side. So that's bearings. A little bit more application in this particular section involves harmonic motion. So here's a display involving some harmonic motion. So what we see in this particular website is a pendulum swinging back and forth, and there's the shadow of the pendulum. You can see a spring moving back and forth, so simple harmonic motion for a spring, a weight on a spring. And then also we have what's called uniform circular motion, which is the weight going around in uniform circular motion, so the same acceleration the whole way around. And the idea now is what do all those things have in common? And what we can do is take a look at them and look at the motion that they translate to. Actually, this is particles in a violin is the idea. So that's also simple harmonic motion. But what we see here is that the spring goes back and forth in such a way that you get these sine waves, which of course now relates to trigonometry. We'll see the same thing if we look at, say, the pendulum motion, as the pendulum swings back and forth, and we would see the same thing with uniform circular motion as well. So getting into some sample problems now with right triangle trigonometry applications. This is page 338, number 21. We have a point 50 feet in front of a church. Angles of elevation to the top of the steeple and the top of the church, or base of the steeple, and the top of the steeple are these angles here. And so first we draw right triangles that explain kind of the situation. So this is a distance of 50 away. This angle is 47 degrees and 40 minutes, which is basically 47.6 repeating. It's 47 2/3 this angle. And then the angle to the top of the church, the bottom of the steeple, is 35 degrees. And we want to find trig functions to describe this and just get the height of the steeples. This is similar to the example in the book. So the tangent of 35 degrees is c over 50. That's using the smaller triangle. And we solve for c. And then we look at the bigger triangle. Tangent of 47.6 is the entire opposite, c plus s over 50. And we can solve that for s by multiplying 50 to both sides and subtracting c. And of course we could get c from here. This is just doing a lot without the calculator. So s then is 50 tan 47.6 minus 50 tan 35. And just to extend a little farther, but of course you need a calculator eventually, I factored out a 50. And then here you can get the height of the steeple. Okay, this particular problem involves, again, this idea of two different right triangles. We have to use the fact that distance equals rate times time here, because what's going on is that you are down here at your home, you're looking at the plane, it's going 550 miles per hour, and the angle of elevation to the plane at one time is 16 degrees, so that's the black triangle here. And then 1 minute later it's 57 degrees, and you want to approximate the altitude of the plane, that is the height. And so we've got two different triangles. We've got the black one and we've got the blue one. And note that this distance, we don't know what it is, it's d, but the distance that a plane goes in 1 minute at 550 miles per hour is 550 times a 60th, because a minute is a 60th of an hour. And so that allows us to set up a couple triangles. So what we can do is start with tan 57. This is going to be blue triangle, is h over d. And remember, we're trying to solve for h here. So that gives us a way to get h with d in it. And then tan 16 is going to the black triangle, and that is h divided by d plus 550 over 60. So now I've got two equations and two unknowns. And so what I can do is plug in for h tan 57 times d. Now I've just got one unknown, and I'll go ahead and solve this for d. So you need to get the calculator out, solve for d. And then, of course, once we know d, we'd be able to plug it back in and get h. So now I've got d, I'm getting all the way down to where, of course, I've got to use a calculator eventually. So I get this. Now, this is just to simplify some of the quantities I'm writing. And eventually you get 3.23 miles is your height, because you have to keep track of the fact that the units were in miles per hour originally for 550 miles per hour. And so your distances will also be in miles. Okay, this is a problem involving bearings. So surveyor wants to find the distance across a pond. The bearing from A to B is north 32 degrees west. It's important to draw in north. So I draw in red this north line, and here I draw a north-south line. So north 32 degrees west implies that this angle here in blue, 32 degrees. Surveyor walks 50 meters from A, so this is a distance of 50 as shown. And the bearing from C to B is 68, so that means this angle in here is going to be 68 degrees. So now we've got those angles, and the first thing we want to do is find the bearing from A to C. So bearing from A to C, well, we know that if this is 32 and this is a right angle, then this angle must be 58 degrees here because they must be complementary. So the bearing from point A to point C is going to be north 58 degrees towards the east. And then as far as finding the distance from A to B, that's this distance L. And what I've done is, knowing that this is 58, I know this angle down here is also going to be 58 because these are alternate interior angles where you have a transversal and these two lines are parallel, of course, in red. So if we've got 68 here and 58 here, this is a 54-degree angle. And so now I can say the tangent of 54 is equal to opposite divided by adjacent and solve that equation easily enough while multiplying by 50. So one more example. That would be, involves simple harmonic motion. Let's take a look at the problem though, 341.57. Okay, what we have here is d is equal to 1/16 sine of 140 pi t. The idea being that this is describing simple harmonic motion. So first find the maximum displacement. Well, the idea is that no matter what we have in here for a period, the biggest sine it's ever going to get is going to be 1. So 1/16 times 1 will simply be a maximum displacement of 1/16. For part B, we have find the frequency. Well, frequency is 1 divided by the period. Those are reciprocals. And so if you want to find frequency, it's 1 over the period. And if you recall, period for a sine function is 2 pi over b, so frequency would be b over 2 pi. In this case, your b is 140 pi, and so therefore your period will be 70, and it would depend upon the units here, whether it's 70 seconds or what have you. Find the value of d when t is 5. So that's simply plug in 5 for t. So we have 1/16 sine 140 pi times 5, and we get, well, 0, so there's no displacement there. And then lastly, find the least positive value of t for which d is 0. Well, d will be 0 when t is actually 0, but that's not positive. So we want to find the next place where it's positive, and realizing that a sine function basically looks like this, we're looking for this value. So we're looking for half a period. And so knowing that a period is 70, 1/2 of a period, and so this will be 1 over 140 will be the time that we would want to put in.